Today in the workshop, we're working with the I2C bus again. I'll show you two ways to interface a 3.3 volt logic Raspberry Pi with a 5 volt logic Arduino. We're changing levels today, so welcome to the workshop. Hello and welcome to the workshop, and we are back working with I2C or I2C or IIC or TWI, the integrated circuit bus. Now the fact that this bus has a number of different names and none of them have actually been standardized except of course for integrated circuit bus is just one of the many discrepancies you'll find when you're working with I2C. Another thing that you will find is that there is no standard connector for I2C. Unlike things like USB, there are a variety of connectors you can use. There is a small Molex connector that many manufacturers have latched onto, but it's by no means a standard. A lot of people also simply use DuPont pins, and even in that case, there's no standard as to what the pinout is. I have a number of I2C modules, and they have the same 4 pins, but they're not necessarily in the same order. Another thing about the I2C bus that varies is the voltage levels that we can use. Now the two most common levels are 5 volts and 3.3 volts. Now most of these discrepancies are things that we can get around quite easily. Obviously the name is really irrelevant. We can call it Bill's bus and it'll work just as well. And with the pinouts and that, as long as we know what 4 pins are connected to what, we can connect everything together and that will work fine. But in terms of voltage, that's a different story. It's a very common application to have interface 5 volt and 3.3 volt logic, and since I2C can use both of them, you'll find yourself in that situation many times, and one of the most common situations is interfacing an Arduino with a Raspberry Pi. The Raspberry Pi uses 3.3 volt logic on its GPIO bus, whereas most Arduinos use 5 volts, although there are 3.3 volt Arduinos as well. Now this is a really common application because it creates quite a powerful combination. The Raspberry Pi, of course, is a full-fledged microcomputer capable of running Python, capable of connecting to the internet natively. Most Raspberry Pis have Bluetooth and Wi-Fi on them. They're very powerful, but one thing that they aren't powerful at is at I/O, and this is where the Arduinos excel. Arduinos are basically built for I/O. They have several digital I/O ports. They have analog to digital converters. They can handle interrupts. They can do timing very precisely. So by putting the two of them together, you can get a very powerful combination, and that's what we're going to do today. So today we're going to look at 2 different ways of interfacing a Raspberry Pi to an Arduino and handling the difference between their 3.3 volt and 5 volt logic. So what we're going to do right now is take a look at the situation with 3.3 volts and 5 volt logic, see what concerns we might have with it, and then we'll take a look at the Raspberry Pi and the Arduino and see a couple of different ways to hook them up and run the same test program with both methods. So let's get going. So let's examine I2C voltage level conversion. I2C can be run at different logic voltage levels. The most common voltages are 3.3 volts and 5 volts. The I2C voltage is determined by the voltage of the master device. The SDA and SCL lines need to be pulled up with a pull-up resistor to the master voltage level. Now here are the rules regarding connecting 3.3 volts to 5 volts. A 3.3 volt output can be safely connected to a 5 volt input, and because 3.3 volts is above the minimum threshold required, it will work correctly. A 5 volt output, however, cannot be connected to a 3.3 volt input. It will damage the 3.3 volt logic device. The Raspberry Pi uses 3.3 volt logic. The Arduino Uno uses 5 volt logic. In this scenario, the Pi can work as a master device, and this is the normal case. As a master, the direct connection is possible because the Pi is determining the voltage. You need to ensure that no extra pull-ups or 5-volt I2C devices are connected into this arrangement. The Arduino cannot be directly connected to the Pi as a master. In order to do this, you require a logic level converter. Here's an example of a bidirectional logic level converter. On one side we have a 3.3 volt power connection, and on the other side a 5 volt power connection. On the 3.3 volt side we have the logic A input-output, and this connects through to the 5 volt logic A input-output. The 3.3 volt logic B input-output pin is connected through to the 5 volt logic B input-output pin. And finally, there are 2 ground pins. A bidirectional logic level converter changes the logic voltage so 2 devices of different logic levels can be operated and interface safely. You must use a bidirectional converter for the I2C data line because the data needs to travel in both directions. These devices are available in 2, 4, or 8-channel designs. Logic level converters are a very inexpensive solution to logic level problems. We've already used I2C with the Arduino many times, and it's a pretty simple matter. There are 2 pins defined as SDA and SCL. On the Arduino Uno, they use the address pins A4 and A5. On different models of Arduinos, they may use 2 different pins, but once we know what these pins are, we can pretty well get going in connecting our I2C devices. However, there are a few additional considerations when using I2C with a Raspberry Pi. When you look at the Raspberry Pi GPIO, you might notice there are actually 2 I2C buses. One is labeled I2C0 and one is labeled I2C1. Now when you first see this, you might get the idea that, hey, I've got 2 independent buses, I can take the same sensor, take 2 of them, put them onto the different buses, and still read them even though they have the same addresses because it's 2 independent buses. Well, that is actually not true. The I2C0 bus on the Raspberry Pi is exclusively for reading an EEPROM that is located on a Raspberry Pi hat. A hat is hardware attached on top. It's the expansion cards that you can attach to the Raspberry Pi, similar to a shield on an Arduino. Now, that expansion card will have a little EEPROM on it, and it identifies what the card actually is, and so the software can go and configure itself correctly. That's the only reason the I2C0 bus is there. You cannot use it for anything else. So you need to use the I2C1 bus, which of course is a 3.3 volt I2C bus. Another consideration is that when you first install Raspbian, the operating system that most of us use on the Pi, the I2C bus is actually not enabled, and you have to go through and enable it. So right now what I'm going to do is show you how we set up the Raspberry Pi, and then we can get started with our experiments. In order to set up your Raspberry Pi, you're going to need to get a copy of the Raspbian operating system and install it on a micro SD card. Now, the current version of Raspbian as of this recording is Raspbian Buster, and there are 3 versions of Buster available on the raspberrypi.org website. I chose Raspbian Buster with desktop because it's very easy to work with having a full-fledged desktop, and it's probably the best choice for you as well. You can also elect to choose Raspbian Buster with desktop and recommended software, and you'll get some additional software utilities including the LibreOffice suite, but this is not necessary for our program, so it's up to you which of these 2 you wish to download. Download the zip file, and then you're going to need to install that onto a micro SD card. Now, the simplest program that I've found for doing that is something called Etcher. It's a free program that you can download for any operating system, and it makes installing images onto a micro SD card very, very simple. And those of you who've watched my videos have seen me install and use Etcher several times before, so I won't repeat myself here. But get your Raspbian copy, install it on a micro SD, and insert the micro SD into your Raspberry Pi, and we're ready to go. When you first install Raspbian and boot it up, you're going to be asked a number of questions in order to set the operating system up. These are questions as to the location that you're in, the type of keyboard, your time zone, etc., etc. You'll also be given the opportunity, if you wish, to set up a Wi-Fi connection, which you can certainly do, although it's not required for the experiments that we are going to be doing. Once you've done that, however, you're still not finished because we still need to activate the I2C connections on the Raspberry Pi because by default they do not come activated. In order to do that, you'll need to open a terminal, which is this icon over here. Once you have it opened, you're going to need to bring up the configuration utility, and you type the following in order to do that. sudo, S-U-D-O, space, Raspi, R-A-S-P-I -config, C-O-N-F-I-G, and hit enter. And this will bring the configuration utility up. Now, I've already configured mine, but I'll show you what you need to do in order to configure yours. You can use your arrow keys to navigate down into interface options and then hit the enter key. And then in the interface options, you'll notice a number of the accessories that you can activate for your Pi. Now, by default, these are all disabled, but we want to enable the I2C in this case. So we'll go down over here to I2C and again hit enter. Now, in my case, I have already got the interface enabled, but in your case, it'll come up as no. And so you can use your keyboard and your tab key in order to navigate to yes, and then press enter. And then you can say OK. And then you can navigate down here using your tab key and your arrow key in order to go finish. Now, in previous versions of Raspbian, you would have to reboot after this point, but it seems that with the current one, that is not necessary. However, you can do that, of course, if you wish. Now, in order to test to see that the port is enabled, there's a simple way of doing that. You can use an ls command, which is the command that Linux uses in order to list directory contents. So if you do ls space /dev space star I2C star and hit enter, you should get this result with I2C-1, and that indicates that the I2C-1 port is now available. And if you've done this, you have now successfully set up your Raspberry Pi for our I2C experiments. So now that we have our Raspberry Pi set up, we're ready to begin our experiments. Now, as I said earlier, we are going to do the same experiment twice with two different hookup configurations. And the first one we're going to look at is hooking the Arduino and Raspberry Pi directly together. Now, we can do this because, as you recall, it is the I2C bus master that determines the voltage levels, and in all our configurations, the Raspberry Pi is going to be the master, and that is indeed the most common configuration that you'll have. Now, the Raspberry Pi has a couple of pull-up resistors on its GPIO, and they pull it up to the 3.3 volt level. Because the Arduino uses open collector outputs, its output will also be pulled up to only 3.3 volts, so that on the data line, when it returns data, it will be returning it at 3.3 and not 5 volts. Now, this setup will work. However, you need to be cautioned if you are going to add additional I2C devices to make certain that there are no devices with pull-up resistors that will pull the lines up to 5 volts, because if that's the case, then you will harm or possibly destroy your Raspberry Pi, which is not something you want to do. So let's take a look at the hookup right now for our first experiment, and then we'll look at the code for both the Arduino and the Pi that we'll need to communicate. Now, for the first experiment, you are going to need a Raspberry Pi, and you can use any model of the Raspberry Pi that you wish. You'll also need an Arduino Uno. Optionally, you can use an LED and a dropping resistor for the LED. I use 220 ohms, but any value from 150 to 470 would be sufficient. Again, these two components are optional. We'll begin by tying the ground of the Arduino and the ground of the Raspberry Pi together. Now there are several ground pins on each device. I used pin 20 on the Raspberry Pi and tied it to one of Arduino's grounds. The SDA line on the Raspberry Pi is pin 3 on the GPIO, and this is connected to pin A4 on the Arduino Uno. The SCL line is pin 5 on the Raspberry Pi GPIO, and it connects to pin A5 on the Arduino. If you're using the LED, connect the anode of the LED through the dropping resistor to pin 13 on the Arduino, and then ground the cathode of the LED. And this completes the hookup. Now here's the code that we're going to use on the Arduino side. Now this is very simple code because all we are doing is accepting signals on the I2C bus from the Raspberry Pi and using them to toggle the built-in LED on pin 13 on and off. So we'll start our code out by using the wire library. The wire library, of course, is the I2C library for the Arduino, and this is built into your Arduino IDE, so you will not need to add an additional library. We'll also define a constant for the LED that we have on pin 13, and we call that LED pin. Now in this setup, we're going to join the I2C bus as a slave with address 8. So when you do a wire begin and pass an address to it, it tells the wire library that we're going to be operating the Arduino as a slave and not as a master. We'll also use the onReceive to call a function that we call receive event, which we'll take a look at in a moment. So every time we receive data, we will call the receive event function. And then we're going to set the LED pin up as an output, and we're going to set it low so that the LED is off. Now here's the receive event function itself. Now we are going to receive the event, and it has a parameter called how many events we are going to get. And while the wire is available, we are going to read the wire, and then we're simply going to write the value to the LED pins. So since we're going to be using values of 0 or 1, that will toggle the LED on and off. Now in our loop, there isn't very much. All we're doing is running a delay, and basically we are really just waiting for data on the I2C line so that we can run the receive event function. And so now that you've seen the code, let's go and take a look at the Raspberry Pi code. Now here's the program we are going to be using on the Raspberry Pi side for our experiments, and we're writing this in Python. Now you can use a number of different editors for Python. I'm using the Genie editor, which is included in the Raspbian distribution, and Genie just happens to be one of my favorite text editors anyway, but you can use a different one if you wish. Now we're going to start off by importing SMBus from the SMBus library, and this is the library we need to work with I2C. We're going to set a variable called ADDR, and we're going to set it to the bus address, the address of our slave, which in our case is 8. Remember, the 0x indicates it's hexadecimal, although with the number 8 that really doesn't make a difference because a decimal 8 and a hexadecimal 8 are actually the same thing. And then we're going to set up a variable called bus, and it's an object using the SMBus number 1, and that indicates that we're going to be using the I2C1 connections on the Raspberry Pi. Now remember that the Raspberry Pi actually has an I2C0, but that's exclusively reserved for using hats. I also have a variable that I call num, and I set it to 1. It's going to be used in the while loop right below this. Then I print to the screen some instructions, so it's enter 1 for on or 0 for off, and that's how our program is going to work. When we type in the number 1, it is going to send a 1 down the line and turn our LED on. If I type in a 0, it will turn it off. And so while num equals 1, which it does in this case, I'm going to get an input and assign it to the LED state variable. Now the input command also has a parameter in which I can have some text, and I just chose to use a number of greater than signs as a prompt. Now, if the LED state equals 1, and that's this value over here, now notice that the 1 is captured within quotation marks. That means the key 1 as opposed to the value 1. There's quite a difference. So if we press the key that is labeled 1, then we are going to write to the I2C bus that value, and here's the value we're going to write, and that will switch the LED on. If we enter a 0, on the other hand, we're going to send a 0 down the bus and switch the LED off. If we type anything else in, we're going to change the num variable to a different value other than 1, and now this while loop will evaluate as false, and that will end our program. So we can continue to toggle our LED by typing 1s and 0s, and when we're done with that, we just type something else, and that will end the program. And so there we have it, the simple Python program that we are going to be using in order to test our I2C connection. Now here's our simple demonstration. The hookup between the Pi and the Arduino, of course, is quite simple. I've tied the SDA and SCL lines to each other. Make sure you don't reverse these. And I've also tied two of the grounds together. Now, there are several ground connections on the Raspberry Pi GPIO pins, as well as several on the Arduino, and you can use any two you want. I've also got my LED and dropping resistor tied to pin 13 on the Arduino. Of course, this is optional. You could just elect to use the built-in LED in the Arduino, and that would work fine as well. So now let's take a look at the Raspberry Pi desktop. Now I'm going to open a terminal window. Now I have placed my Python program into the Documents folder, and so I'm going to need to change into that first. And if I do a listing, I will see my Python program. There's another one in there that I was using earlier that we'll just ignore. And you just need to type Python 3 and then the name of the program you're using. And this will run our program, which is displaying enter 1 for on or 0 for off. So I'll enter a 1, and as you can see, our LED is indeed illuminated. And if I enter 0, the LED is turned off. And I can continue to do this as much as I wish. If I enter any other value other than 1 or 0, the program will end. And so it's a very simple demonstration, but remember, we are controlling this LED, which is on the Arduino, using I2C from the Raspberry Pi. So as we see, hooking an Arduino and a Raspberry Pi directly together will work for communications on the I2C bus, providing that you pay attention to pull-up resistors and have nothing that is going to pull it up to 5 volts. However, it's not the ideal situation. For one thing, I2C can only really drive a cable of about 1 meter or so. After all, it was originally designed as to be used within the confines of a printed circuit board. But with the setup that we have right now, I think you're going to find you won't even be able to get that meter. It's kind of operating on the threshold. Another issue comes if you're building a product and create an external I2C connection. That creates the possibility that someone might connect a device that is 5 volts and has a pull-up resistor, and that of course will go and destroy your Raspberry Pi, which is not a good thing. There is a solution to this, and it's called a bidirectional data converter. A bidirectional data converter simply converts data from one voltage level to another level, and because it's bidirectional, the data can flow in either direction. So we will use a converter that converts 3.3 volt logic into 5 volt logic and can do it in both directions. It can also convert the 5 volt to 3.3. Now, bidirectional data converters are very inexpensive devices. You can make your own using a MOSFET, but since you can get a little one for less than 50 cents, it's probably the route you're going to go. So let's take a look at a bidirectional data converter first, and then we'll see how we wire it into a circuit between the Arduino and Raspberry Pi, and we'll repeat the same experiment and hopefully get the same results. Let's take a look at a couple of these logic converters. Now, these are very simple devices, and they're usually sold without the pins on them. I've got another one that I've soldered a few pins onto as well. And as you can see, they're very tiny, and they basically have 2 sets of connections on them. They have the connections on one side for the 5 volt stuff, and the other side for the 3.3 volt stuff. And that's really about all there is to these things. Now, they're very, very inexpensive. You should be able to pick up a handful of these things for a couple of dollars. And for 3.3 volt to 5 volt logic applications, these things are great. Now, these are dual channel bidirectional converters. You can also get 4-channel and 8-channel ones if you wish. Just make certain when you are getting a converter, you are getting a bidirectional converter, a converter that can handle data going in either direction. There are unidirectional ones that have a specific input and an output, and that won't work on the I2C data line, because the I2C data line, of course, can be sending or receiving data. So definitely get the bidirectional sort, but otherwise there's really not too much more to the logic converters. Now for this hookup, we're going to start with the same components we used before. I'm not showing the LED and dropping resistor, but you can leave these connected to the Arduino if you hooked them up in the first experiment. We're also going to add a 2-channel bidirectional logic level converter. Now first we'll hook our Raspberry Pi up to the logic level converter. So connect the ground on the Raspberry Pi, which I'm using on pin 20 of the GPIO, to the ground pin on the 3.3 volt side of the logic level converter. Connect the SDA line, which is pin 3 on the GPIO, to the 3A input on your converter. The SCL line, which is pin 5 on the GPIO, will be connected to the 3B line on the converter. And the voltage, the 3.3 volts, which you can get from pin 1 of the GPIO, will be connected to the V3, or the 3.3 volt VCC, on your converter. Now on the Arduino side, we'll make the equivalent connections. So we will connect the ground on the 5 volt side to the Arduino's ground. The SDA, which is pin A4 on the Arduino, is connected to the 5A line on the logic level converter. The SCL, which is pin A5 on the Arduino, is connected to the 5B line on the converter. And finally, the converter's 5 volt input comes directly from the Arduino's 5 volt output. And again, you can still leave the LED and dropping resistor intact. And so now that you've got that hooked up, let's go and give it a test. And once again, we're back with our demonstration, this time using the logic level converter device, which you can see over here on my solderless breadboard. And of course, I've got the 5 volt side of this powered by the Arduino Uno, and the 3.3 volt side powered by the Raspberry Pi, and my LED is still in the same place it was for the last demonstration. So I'm running our Python program, our very simple demonstration program. I'm going to hit a 1 and press enter, and as you can see, indeed, it does turn the LED on. Giving it a 0 will turn it off. And of course, I can continue to toggle the LED as much as I wish. And again, a very simple demonstration of the I2C capabilities between the Raspberry Pi and the Arduino, only this time using a logic level converter. So this brings us to the conclusion of today's video on I2C, but it is not the last time we're going to look at I2C. I'm going to do one more I2C video, and you'll see it in a couple of weeks. What we're going to cover next time we talk about I2C is some more advanced topics, including using multiple I2C masters on the same bus, and extending the I2C bus so that you can use devices that are separated by more than a meter. So keep your eyes out for that video. Now, the best way to find out about that video and about any new videos that I do here in the DroneBot Workshop is to subscribe to the YouTube channel. So if you haven't done that, please click the little thing just below the video to subscribe. You can also click on that little robot in the corner, and he'll do the job of subscribing for you. Now, you will find an article accompanying this video on the DroneBot Workshop website, and there's a link to that article below. You'll also find a lot of other great tutorials and projects on the website, and to keep up to date with that, the best way of doing that is to subscribe to the DroneBot Workshop newsletter. It's not a sales letter, just an occasional letter I send you out to let you know what's going on in the workshop, and you can subscribe to the newsletter when you're on the website. And finally, if you want to discuss anything that we've talked talked about today with myself or with other enthusiasts just like you, the best way of doing that is to go to the DroneBot Workshop forum, and you will find a link to that below. So there are lots of ways that we can dialogue about I2C and other subjects. So until the next time we meet, please take good care of yourselves, and I hope to see you again very, very soon here in the DroneBot Workshop. Goodbye for now.